Welcome back to ME 760 Engineering Analysis 1. So last time we were just discussing the determinants of matrices and how to get the inverse of the determinants and inverse of a matrix using determinants. And now we will conclude this part by just giving the properties for the inverse of a matrix. So the first property for the inverse is if you have a matrix A and you take the inverse, then you take the inverse again, you will get back to the same matrix A. So this is very trivial, very simple. If you have a matrix and then you take the transpose of the matrix and then you take the inverse, this will be as if you take the inverse first and then transpose it. And when you transposing the matrix will be just rotating the matrix so that you will make the rows columns and columns will be rows. So if you have a product of two matrices A, B, and you want to take the inverse, this will be the inverse of B multiplied by the inverse of A. So you just flip the order of the multiplication. If you have multiplication of couple of matrices A up to G and you take the inverse of this multiplication, this will give you the last matrix first, then the first matrix last. So it's exactly like this one. So instead of just flipping B to come before A, you will flip the last matrix will come first, and then the matrix behind it will come second, and so on until you get the last matrix here. So those are the properties of matrices, of inverse of matrices. Now we will define the trace. Sometimes they call it the spur of a matrix, and it is defined as the trace of a matrix is just defined as the summation of all the diagonal terms for the matrix from 1 to n. So if you have a matrix A11, A12 up to A1n, this is A22, A33, and this is AN1 up to ANN. All what you want to do to get the spur is just to add those elements here in the diagonal, and that's it. And the trace of A plus minus B, if you have addition or subtraction for two matrices, will be just the trace of A plus or minus the trace of B. And the trace of multiplication of AB will be just the summation of AB II. I think the proof is in the book. So now we will switch gears and we will talk about operators. So linear operators, sometimes they call it linear transforms, and sometimes they call it mapping. We do mapping. So what do we mean by linear operators or linear transformation? So let's assume that I have a vector space X capital here, and I have another vector space Y capital, and you have some element here x1 that with the operation, certain operation, you will map it to the other vector space y1. You have another x2 element here, or vector, that with another operation you will map it to y2, something like this. So we call mapping or transformation, and we define it as follows. So a transformation or mapping F will take every vector x in the vector space x capital into unique vector y in the vector space y capital. And usually, mathematically, we write it as f for the vector x will give us y. So you have, usually you call f a transformation or operator or mapping of element x, and it gives us the element y in the vector space capital Y. Sometimes you will find it written as y equal to f x. And for a transformation to be linear, two conditions must be satisfied. The first condition is if you have a transformation on vector x1 plus vector x2, it is equivalent to the transformation of x1 only plus the transformation over x2 only. So it's linear transformation. And the other condition is if you have a transformation for a constant, whether it is real or complex, multiplied by a vector x, should give you the same constant multiplied by the transformation of the vector x. So do you have any questions so far? Just simple definitions. So now let's look for examples for some transformations. So if we have M by N matrix, A, this will transform vector x in the real vector space, with dimension n, into real vector space with dimension m. How? Let's assume that we have A11, the first element, A12 up to A1n, and then we have m rows, so this will be AM1, AM2 up to AMN. We have n columns and m rows. and you have another vector x1, x2, x. Should be n or m here. We stated before to multiply two matrices. If this is m by n, this is definitely how many rows? N by 1. So this will transform this to what? To y1 up to y what? M. So this is m by 1. So you have to have n's equal, yes, and then we'll give you the remaining m and 1. So what happened for the matrix here? A matrix m and n, when you apply the matrix over a vector in the real dimension vector space with dimension n, will transform it to another real dimension vector space with dimension m. What's the real dimension vector space? Real vector space? It's the vector space that has all real numbers, and you knew real numbers are integers and what? Huh? Everything contains the integer and the decimals and contain the complex and everything. So this is the real space. But what's the dimension for the real space? It's the total number of linearly independent vectors in the space will give you the dimension. If you remember from a couple of lectures ago, when we talk about vector spaces, we try to say how many vectors we can write as linearly independent, and the maximum set of linearly independent vectors give you the dimension of the vector space. So this is just one of the examples here. Another example, if, for example, I ask you to find the transformation that will transform a vector with two components, x1 and x2, will transform it to 3x1 minus 2x2 and 2x1 plus 3x2. So we need to know what's the transformation that can transform a row vector like this, or a vector like this, row or column vector, to a vector like this. So you will find that this transformation is a matrix given by 3, 1, 2, 3, and then you have x1, x2. When you perform the multiplication, you will say this is multiplied by x1, so it will be 3x1, and this is multiplied by x2, and you add them together, so it will be negative x2. And again, this is multiplied by the first one, will give you 2x1, and this is multiplied by the second one, will give you plus 3x2. And this will be what? y1 and y2. Did you understand? So all what you do is we find the transformation that will transform this vector from x1, x2 to another vector 3x1 minus 2x2, and the other component is 2x1 plus 3x2. So what we did is we find the matrix that will transform it to this, and this is the matrix here. Clearly this is the matrix. Do you think this is a linear transformation or not, and why? Here is the definition for linear transformation. So if we apply with this one over x1 alone, and apply over x2 alone, then if we apply over x1 plus x2, we'll get the same result. And then if you multiply a matrix by a constant, you can take the constant out, and it'll give you f multiplied by or operated over x. So it is a linear transformation. The two conditions will hold. Another example, for example, to look at instead of matrices, if we define V, a vector space, to be a set of all functions, that belong functions of t, where t goes from 0 to infinity, so that when you integrate from 0 to infinity for those function f of t dt, this will be definite. It's less than infinity, so definite. So if we take an operator and we apply this operator over the function f of t, so that this operator will be just the integration from 0. So operators or transformation can be anything. Can be matrix as an operator, can be differentiation as an operator, can be integration as an operator, can be anything. So just the transformation is you will use operator, and operator is just any mathematical operation, whether you differentiate, you integrate, you do Laplace transform, you do del square like this. Any of those operators or mathematical entities are called operators. So when you apply this operator, for example, our operator now will be over the functions, f of t will be from 0 to infinity, and we will multiply the function by s e to the power of st multiplied by the function f of t dt. And in this case, you will obtain what we call f of s. Anybody knows what's this? It's the Laplace transform. Any questions so far? So now let's focus our attention to matrix transformation. So instead of just we'll use, for example, the transformation as, let's say, integration or differentiation or anything. Let's focus our attention to just matrix, the operation over matrices, and let's define the eigenvalue problem here. So generally, if you have vector space, and you have inside this vector space, let's say, an element f, and within certain operation, you transform this vector f to another vector g inside the same vector space. So you did not transform the vector from one vector space to another, but rather you keep the same or the new vector inside, or the new element inside the same vector space. So an operator O we call it maps a function or vector of a vector space. So it maps f of a vector space into another function or vector g in the same space. And in this case, we'll call operator O, if you apply it over the function or vector f of x, will give you g of x. We can give examples for certain operators that we can use, for example, to transform some functions. One of those operators, operator O, is 1 over x dx. So this is the operator. And let's say f of x in this case is x to the power of 4. So you have a function x to the power of 4 in a vector space, and you have this operator. So now if you apply the operator over the function f of x, this will give you what? 1 over x, and this is the function now dx. So this will give you what? This will give you x to the power of what? 3. And this will give you 1 over 4 x to the power of 4. So just, we will see in a minute, this operator, what it did for the function, it reproduced the same function but with another constant in front of the function. And we will see in a minute that this is a definition of eigenvalue problem. That you have an operator, you apply the operator over a vector space or a function, and then you will get the same vector or the same function with some constant multiplied by the function. Another operator is the second differentiation operator, and if we apply it over x to the power of 4, this will give us 12x squared. Another operator is a matrix -5, 2, 2, -2. And when you operate this matrix over x1, x2, this will give us -5x1 plus 2x2 and 2x1 minus 2x2. So sometime there exists certain functions f of x that are mapped into multiple of themselves. And if we operate over certain functions f of x, we'll get just multiple of the same function f of x. And those functions will define, this is what define the eigenvalue problems. So you have operator, whether the operator is a mathematical operator like differentiation, integration, Laplace transform, whatever the operator is, or matrix, and you operate over, let's say, a vector or a function. When we define the linear vector spaces, we said that the elements of the linear vector spaces are either functions or vectors, any elements you can put in the vector space. So when you operate over a function, you will obtain multiple of the same function. So instead of just operating over a function and you obtain a completely different function, this is not an eigenvalue problem. So the eigenvalue problem will be whenever you have operator operated over a function, you will obtain multiple of the same function. This is an eigenvalue problem. So there's a couple of definitions here we have to define before we go in depth on the eigenvalue problem. So generally, this is a mathematical equation. Yes? So generally, this mathematical equation will have generally has only trivial solution, trivial solution for an arbitrary value for lambda. So not every value of lambda will give you a solution for this equation. So generally, if you put any arbitrary lambda, you said lambda is 4.5 or 3.8. So you will not get anything that will satisfy the equation other than the trivial solution. And what's the trivial solution? F of x equals 0. So 0 multiplied by anything is 0 multiplied by anything, so the equation will be valid. So generally, we'll get the trivial solution for any arbitrary value for lambda, and only for very specific lambdas. Lambda, the non-trivial solution can be obtained. And usually we call when we find non-trivial solutions for specific values of lambda, we call those lambda the eigenvalues. So we call such lambdas the eigenvalues of the operator O, and usually write them like this. Maybe you will have one eigenvalue, or maybe you will have n eigenvalue, and so on. We will see in a minute maybe how to get those eigenvalues. And the associated functions of vectors, or vectors are usually called the eigenvectors or functions. Eigenvectors / functions. And usually they are given again between the brackets here, Fn of x. And usually the eigenvectors, sometimes also they are called eigenmodes, or simply they are called also modes. So let's take an example here. If we have an operator O, which is d by dx, such that d by dx, which is the operator, if you apply it over a function f of x, will give you lambda n multiplied by f of x. Can you think of an example of what function, if I just differentiate the function, will give me the same function with a constant front? Exponential function. And what else? Okay, so let's think about the exponential function. So f of x is equal to a multiplied by e to the power of lambda n multiplied by x. So if you differentiate this once, this will give you a multiplied by lambda n multiplied by e to the power of lambda n x. A e to the power of lambda n x will be f of x. So this will give you lambda n multiplied by f of x. So for any number, real number, lambda n, real or complex, you will have this valid transformation. Do you have any questions so far? Is there anything that you do not understand so far? Okay. So as a generalization for the eigenvalue problem here, we also can write it as the following. We can write it the following. We can write operator O1 applied over the function f of x will give us lambda, and there is another operator O2 operated over the function f of x again. So this is another form of this one. Why do you think they are equivalent?
Because you could write O1 and O2 as just one function, one operator.
You are very near. So you have to take the inverse of O2. Yes? So you can write the inverse of O2 and bring it here. So inverse of O2, you can write O2 minus 1 here. And O1, because if you apply O2 inverse, operator O2 inverse, over both sides, this will give you O2 inverse and O2 f of x. What's O2 inverse operated over O2? 1. So if you differentiate a function, then integrate it, you will get the same function. Yes? So this is 1, so this will give you lambda f of x, and this is another operator, we'll call it O, multiplied by f of x. So now we will focus our attention now for the eigenvalue problem for matrices, and we will look for eigenvalue for matrices. So matrix eigenvalue. So from now on, the operator O will be just a real matrix. So this is matrix with real elements, let's say. So now, how can we write the equation here in terms of the matrix? It will be what? The operator O is replaced by A. So this is A multiplied by a vector now instead of function. A vector x is equal to lambda multiplied by the same vector x. So this is the eigenvalue for the matrices. Again, this can be written as, if you come here, we can write AX equal to lambda. If you multiply the identity matrix by the vector x, it will still give you the same vector x. And then this can be AX minus A minus lambda I operated over x equal to 0. So this is called the characteristic equation. Characteristic equation. So if you remember at the very early beginning in the first lecture when I give you the quiz, I ask you to get what's the eigenvalues for a matrix. And this is how you will get the eigenvalues for a matrix. You will form the characteristic equation, then you will solve it, and you will get the eigenvalues. And we will see an example now. So this is an equation, yes? A matrix, instead of a matrix A, now we have a matrix A minus lambda I. Yes, guys? So if A is A11 up to A1n and AN1 up to ANN, and we'll have A22, A33 up to here. When you subtract from this matrix lambda, and then the identity is what? 1, 1, 1, 1, 1, all zeros, all zeros. So when you do this, you will just take A11 minus lambda 1 will be the first element. So this will give you what? A11 minus lambda 1. Second element, lambda by 0 is 0. You subtract it from second element, you do not get anything. So A12 will be the same until A1n. You will do the same everywhere, will be the same, but the diagonal will be only change it. So this will be ANN minus lambda. This is lambda 1 or lambda minus lambda. There's no lambda 1, minus lambda. And then you will have second element will be what? A22 minus lambda, A33 minus lambda, and so on. So this is the new equation now. So this is the new matrix now. So this is a matrix, yes? And this is an equation. Matrix multiplied by a vector x1, x2 equal to 0. Last time we stated that this is a homogeneous or inhomogeneous equation. Homogeneous, why? Because it is equal to 0. And I mentioned last time that if you have A multiplied by X equal to 0, I said you have two situations. Either X is equal to 0 and A does not equal to 0, and in this case this is the what? Trivial solution. All the vector will be zeros. But you do not need the trivial solution. So if you do not need the trivial solution, you rather keep X not equal to 0, but the determinant of A should equal to what? 0. So to have a solution for this equation, I should have the determinant of A minus lambda I equal to what? 0. So the determinant of A minus lambda I should be equal to 0 for non-trivial solution to exist. So this is the condition. Any questions so far? So let's go a little bit back to the same matrix that we defined over there. So the matrix here is when you get the determinant for this matrix, yes, you will obtain, if you try to solve it using, let's say, the row or the vector or even the diagonal or whatever. So when you try to solve it, you will have elements multiplied by each other, yes, and you will have lambdas. So how many lambdas you will have? 1, 2, 3, n. And this will give you a polynomial, yes? So this will give you a polynomial, and what's the degree of the polynomial? N. A polynomial of degree what? N, and lambdas will be of an order n, degree n. So this will give you a polynomial of degree n, and all the coefficients of this polynomial are real number. So let's get an example. I want all of you to concentrate on this example because this will clarify a lot how we will get the eigenvalue for a matrix and so on. If you don't understand anything, please stop me and I will be more than happy to help again. A is equal to -5, 2, 2, -2. If I ask you what's the eigenvalues and eigen functions or eigenvectors of this matrix, so the first thing is you try to solve what? The characteristic equation. So what's the characteristic equation? Determinant of A minus lambda what? Lambda I is equal to what? Is 0. Let's form the determinants. So the determinants will be what? The first element will subtract lambda from the first element. From all the diagonal, yes? But because we have 2 by 2, the diagonal will be what? -5 and -2. So this will be -2 minus lambda, and then we will have the other elements not changed. So far, did you understand? So let's take the determinant, this determinant. So this determinant, we should equate it to 0. So now, what's the determinant now? It's this element by this element minus this element by this element. So it will be what? -5 minus lambda times -2 minus lambda minus 4 equal to 0. So if you just expand this one, will give you lambda square plus 7 lambda plus 6 equal to 0. So if you just do decomposition for this equation, this will give you lambda plus 1 and lambda plus 6. So now lambda 1 is equal to -1 and lambda 2 is equal to -6. So we got the eigenvalues. So the eigenvalues for the matrix is just -1 and what? -6. So if you remember the first quiz I gave it to you, I asked you for the eigenvalues for the matrix. So just you will come to the matrix and then replace, subtract lambdas from the diagonal, take the determinants for this 1 equal to 0. You solve just an algebraic equation. You will get the two values. Then now we need to calculate the eigenvectors. So how to calculate the eigenvectors? So for every eigenvalue, there is what? Eigenvector here. So let's see here. So we'll write the equation, matrix equation, -5, 2, 2, -2. And this is rated over x1 and x2. Now we want to get this one, and this is equal to, again, matrix over vector equal to lambda over vector. So what's the first one? -1. And x1, x2. So how we'll solve this one? Very easy. Now we will get this one here, and this will be what? This will be -5, 2, 2, -2, x1, x2, plus x1 plus x2. If you do, and this is equal to 0, if you just do the combination here, this will give you -1 plus 2 divided by 2, and this is 2, and this is -2 plus 1, all operated over x1 plus x2 equal to 0. Then this will give you -4, 2, 2, -1, x1, x2 equal to 0. So can you solve this one? -4 by x2 plus what? So -4 x1 plus 2 x what? x2 is equal to what? 0. And the other one is what? x1 minus x2 is equal to what? 0. Can you get the solution here? So you have two equations. So let's assume that x1 is equal to A, and A is any constant. Any constant we'll choose. Then we'll find out that x2 is equal to 2A. Should we leave it like this? We should at least find A is, what A is. So let's assume, so the eigenvector for the eigenvalue of -1 will be written as u1, and it is just A multiplied by what? 1 and 2. So this is the first eigenvector for lambda equal to 1. So usually we will pick up A. So we'll pick up A so that the norm of the vector u1 equal to 1. So it's a unit vector. So when you do this, we will get u1 equal to 1 over the square root of what? Of 5, 1, 2. Okay, guys? Because if you get the norm, what's the norm? Norm of a vector? Square root of its component. Yes? x1 square plus x2 what? Square. And x1 is what? 1 over the square root of 5 multiplied by 1 whole square plus the second one is 2 over the square root of what? 5 whole square under the square root. So this will give you what? This is 1 over 5 plus what? 4 over 5, and this is 1. Okay, guys? So we'll wait here. I will stop here, and next time we will continue. Do you have any questions for today's lecture? Is it easy, or is it difficult, or any questions? Okay, thank you so much, and have a good day.